All right, good morning, students. This lesson is all about plate tectonics. We're going to look at the evidence for plate tectonics. We're going to look at plate motion. There's actually a lot in this lesson to cover, so let's just jump right into this. So when we say plate tectonics, we're really talking about the theory of plate tectonics. And of course, when we use the word theory, we just mean it's an explanation for which there's a lot of evidence to support. And the explanation is really, why does the Earth's surface look the way it does? Or, why does the crust look and also behave the way it does? Why do we see mountains, especially where they are? Why do we see volcanoes? Why do we see even the ocean floor? Parts of the ocean floor look a certain way. Why is that? Why are there earthquakes? And also, it also explains how large areas of crust move relative to one another. So it outlines the motion itself. And part of plate tectonic theory is this idea of a tectonic plate. And what that is basically just a gigantic section of crust that's in motion relative to another plate. So, for instance, if we take the Pacific plate here, we can see its motion relative to the adjacent plates. So, for instance, the Pacific plate relative to the Indo-Australian plate, or the Eurasian plate, or the Philippine plate. So it's all about how is one plate moving relative to another plate. This is a really nice map showing all the tectonic plates, and where we are, obviously North American plate, and we are dead in the center, basically, of this plate. So more on that later and why that's relevant. So how do we even define a plate? How do we know where the edges are? How do we actually figure that out? Well, it all comes down to earthquake locations, where we see active plate motion. So, where are the fault lines, where are the cracks, where are the major cracks at least, and where are the volcanoes? So you kind of put all those together and you come up with basically a plate map. So this is showing earthquakes, in particular, and I'm going to follow along, this Pacific Rim here, and I'm going to show you how it lines up with the other map. So we have the Aleutian Trench here, and we can see just tons of earthquakes. These are magnitude 6 through 9 earthquakes for over 100 years of data. So it comes up here, and it kind of travels down the west coast of the United States. And you can see over here, well, there's the line, right? There's we define the plate line, or the plate boundary. So it comes up, and then it swings back down. And you can even see there's a little ring of earthquakes here. So that tells scientists, oh, well, there must be, that must be its own plate. Every edge of this area is covered in earthquakes. Oh, well, that's the Cocos plate. You can see around the Caribbean here, there's like a little circle here. Well, that's a ring of plate motion. Oh, we'll call that the Caribbean plate. Again, coming down here, we have a much larger ring of earthquakes, but they're much more intense on the east side. Well, why is that? Well, we'll learn about that in a little bit, and that's the Nazca plate. So the earthquakes really define the boundaries. All right, so there are really only 3 types of plate motion, or 3 ways that a plate can move relative to another plate. And I've also outlined here some surface features, especially on the reference table, that go along with that. So a convergent plate boundary is a place where plates collide, and in places where ocean crust is involved, you can get a trench, a deep place that forms from that collision. Under a divergent plate boundary, that's places where the Earth is splitting apart, it's cracking open. If that's happening on ocean crust, that's called a mid-ocean ridge. And transform is just a sliding motion. So you can see all that here in this diagram: splitting apart, divergence, coming together, convergence, and transform. It's a side-to-side sliding, kind of a sliding past each other motion. This is page 5 of the plate tectonic map. And there's a lot to go over on here, so let's just dive right in. Along the bottom, we see a key, and it pretty much tells us everything we have to know. So the arrows show the relative plate motion, so you can see how a plate or how two adjacent plates are moving relative to one another. We could see transform plates, divergent plates. They have a very specific, symbol that's used. We have a conversion plate, which is showing something very specific that I'm going to go over in a minute. And we also have complex or uncertain plate boundaries, and they're probably my favorite because it just goes to show how there's still more to understand. My favorite complex boundary is probably right here, because if you look at the land, nothing about this line matches up with the surface features that are actually present here. So that's just like a made up situation over there. But over here on the east coast of Africa, or the east side of Africa, the East African Rift, that's a very well defined plate boundary. Yes, it is complex or uncertain. However, there is there are well defined plate motions going on there. It is actually divergence that's going on there. The east coast of Africa is actually splitting off, moving off. That would be kind of an interesting sight to see in 50 million years from now. So let's dive into each plate, or each plate boundary. So this is a closer look at convergence. I'm zooming in here on the west coast of America. You can see there's a convergent plate boundary that's happening right off of the coast of Oregon and Washington, and parts of Canada. That's a convergent plate boundary. Convergence with the Cocos plate into parts of Central America, and there's also a small convergent zone that's out in the Caribbean islands. So what is actually going on at these places? Well, at a convergent plate boundary, what you have is denser crust, so a denser plate, and as that denser plate collides with a less dense plate, the more dense plate actually dives down, which makes sense, right? It's more dense. So when they meet, the denser thing goes underneath. And as that happens, as that subduction, it's called subduction, the process, as that happens, you get a deep place, a deep location in the earth. That's called a trench. It's very deep ocean floor. You can also see other things that happen at a convergent plate boundary. Typically, you get magma that's forming. You get volcanoes. You can see a volcanic. There's like a line of volcanoes that are formed. We'll talk about that in another lesson. Okay, so yeah, an ocean trench is a really deep location. The deepest trench in the world, the Mariana Trench, 11,000 meters. That's 33,000 feet down. Very, very, very deep. It's deeper than Mount Everest is tall. So extremely, extremely, extremely deep. All right, we also have the next plate boundary, divergent plate boundary. We have one again off of the west coast of America, off the coast of Oregon and Washington. We have the Juan de Fuca plate that is in divergence with the Pacific plate. We also have a divergent plate boundary all along here. And of course, the most famous one probably, the Mid-Atlantic Ridge. That is a place where we have spreading occurring, and Europe, which is way off the map here, is moving away from America. That's actually splitting apart. Now this gets a little more complicated, so just kind of strap in here. Divergent plate boundaries, we typically find them at mid-ocean ridges, so basically these volcanic mountains, or volcanic high places in the middle of the ocean. And it's places where new ocean crust is actually being created. So we're generating new rock at at those locations. And when we say a mid-ocean ridge, what we're really saying is sea floor spreading. The sea floor, as you can see in this GIF, this very nice GIF, you can see how the sea floor is actually spreading apart, and the magma beneath is moving up, it's solidifying, and it's kind of pushing apart the crust. It actually is a pushing motion. It's pushing the crust apart, and that's seafloor spreading. That's a mid-ocean ridge. Now, why does that happen? Well, there are actually convection currents in the mantle, in the plastic mantle, in the asthenosphere. I said that will come up again. So the asthenosphere, we have convection currents moving upwards and outwards. So that's kind of your pushing force that is pushing the plates apart ripping open the earth and creating new crust. But keep in mind also, while there are places where we have the convection pointing up and out, we also have places where the convection points, where the convection comes together and goes down. So those are places where there's convergence. So we're going to kind of tie this all together now. So places where we have convergence, or plates coming together, the convection points down. It's kind of pulling the ocean crust down. And then we have places where it's moving up and out, moving up and away, and that is a divergent plate boundary. So the mantle convection is really what's driving all of this. The mantle convection, if that wasn't there, if there wasn't a part of the Earth that, didn't have this, flowing, or this kind of flow to it, in the asthenosphere, we wouldn't have plate tectonics. This is kind of putting it all together. This diagram, you can peruse this at your leisure if you want to pause the video. This kind of puts together a lot of the things that I was already talking about. So feel free to pause the video and check out everything that's going on in this diagram. All right, so how do we know that there is seafloor spreading going on? What's the evidence? Well, the best piece of evidence probably is you can sample the rocks down there and you can tell that they're very young. You can look at the temperature of those rocks. They're very hot. And if we look on either side of a divergent plate boundary, you can see that the rocks are older as you get farther away from where they're being created. So they're older over here, they're colder, they're hot, and they're younger over here. Well, there's a symmetry here. That suggests, they must be being created here and then kind of pushing apart and getting older and older as they get farther away. And here is the map that kind of puts it all together. The red is the youngest and the hottest, and the green, blue are the older and colder rocks. So yeah, this really puts it together. It's showing how all along these boundaries, any place where you see red, that's a place of seafloor spreading. Anywhere where you see that, we're generating brand new rocks, brand new ocean crust, and it's spreading apart. All right, so I will pull this up because it actually is, I can't open the file. That's really, really sad. Maybe it's in here anyway. If it's not in here, I'm going to have to show you another time. It's probably not in here. Yeah, I'd have to go find it. I'll just show you something anyway. All along the sea floor, you actually can see the divergent plate boundary. You can see that line there where the divergence is actually occurring. It looks like the seams of a baseball. Comes all the way around. It's pretty clear. It's a very clear crack in the earth where it's occurring. So yeah, divergence is very, very obvious on the ocean floor, for the most part. You can even see it here. This is a very young divergent plate boundary. You can see how these two pieces of land used to fit together. It actually looks like a puzzle, two pieces of a puzzle fitting together. This is a very new divergent plate boundary. It hasn't been around for that long, maybe the last 20 million years or so. So yeah, that's a brand new crack in the earth right there. And this is particularly cool. You can actually see where a new divergent plate boundary is being formed, and these lakes are actually showing the locations of the crack. So all along here is a divergent plate boundary, and this whole section of crust is actually moving east, is cracking off, and you can see all the evidence of that in these lakes. All along here too, there are actually plenty of volcanoes. Also evidence that there is something going on. There's all kinds of hot springs and lots of volcanic activity in this area. Yeah, see a volcano right here. Lots of volcanic activity. More evidence that something is actually happening there. Lots of plate activity. Okay. All right, so how do we actually know that seafloor spreading is happening. One more piece of evidence that I'll give you, and this one's definitely the most challenging of them all. There's actually a magnetic striping pattern that exists about the mid-ocean ridge crust. So you can see here's the ridge. There's the actual place where it's spreading, and you can see the color coding here. It's made it easier to see. The rocks have a magnetic signature, and that magnetic signature is symmetrical. Let's kind of go over how that works, though, because it actually is fairly interesting. The Earth is a big magnet. That's what the Earth is. The outer core of the Earth is churning, and that is what's believed to actually create the the magnetism of the Earth itself. And one thing to know too is that these north and south poles actually flip, and they do it every 100,000 years or so. And we actually know that because the rocks on the ocean floor show this flipping effect, which you can actually see right here. Here's the flipping. You can see, a normal polarity, and then it switches, and then it switches, and it switches. So how does that work? Well, the igneous rocks being solidified at the time, at any given time at a mid-ocean ridge, the rocks there freeze in the Earth's current magnetic, orientation. So we have liquid here. In that liquid, there are iron particles. Those iron particles kind of align themselves to the Earth's magnetic field. Again, because metals can orient themselves with a magnetic field, and when the rock solidifies, it actually solidifies that orientation. So you can see the black stripes here. We're going to call that normal magnetic orientation. So like, say normal is right now. North pole is up, south pole is down. But 100,000 years later, you can see how normal has now switched to reverse. It's flipped. So now when the Earth's magnetic field flips every 100,000 years or so, now a new orientation is recorded in the rocks, and now that's being solidified. And that process will happen over and over and over again. So as the Earth's magnetic field flips, the rocks will freeze in the orientation at the time they were created, and there's your striping pattern. And the striping pattern, what we have to appreciate is that for the most part, it is symmetrical. So that's the big takeaway there. It's a symmetrical pattern. All right, just to finish this up, transform boundaries, probably the least interesting, but certainly not for those people that live in California. The San Andreas Fault is probably the most famous fault line in the United States, and you can see it from even an airplane. It's clear crack in the earth, and I'm going to put in some arrows there to show how the plates are moving relative to one another. So this entire piece of land, which is the entire North American plate, is moving down, and the entire Pacific plate is moving up. It's quite insane if you really consider the magnitude of what we're talking about here, that entire sections of the earth are moving relative to one another. Here's a random fault that I found on Google showing a transform fault in China. You can clearly see how these two mountain ranges used to actually fit together, and they've been cut by this transform fault, and they're just sliding past each other. But you can see by the colors especially that they used to be connected. All right, again, this is another diagram just summarizing all of plate motion. See divergent plates splitting apart. We can see subduction at a convergent plate boundary. We can see an ocean trench. We can see a volcano forming just adjacent to the ocean trench, right next to it, and we can also see a transform fault. This is particularly cool. One thing you can do, along with everything that we've learned in this lesson, but with many other things, you can actually reconstruct what the Earth used to look like in the distant past. And the first image that's going to pop up right now is 600 million years ago. Now we're at 5, 4, 300 million years ago, this is Pangea. 200, the Earth splits, 100 million years ago. And then we're coming up on 50, and we're coming up on the present time. It actually goes by quite quickly. I'm moving through hundreds of millions of years as if it's nothing. And this is called a paleogeographic reconstruction. You can see Pangea there, right? The supercontinent. See how it splits from a divergent plate boundary, right? We can actually reconstruct what the Earth used to look like. It is really quite cool. All right, that's it for today's lesson. That was a longer lesson than usual. There'll be a test result on this, as well as maybe some other things I'll put together.